over here, we will discuss whether an alkyl halide will undergo an SN1 or the SN2 nucleophilic substitution. So let's start with this example. I'll be drawing a methyl chloride. Methyl chloride. Okay. Now, in chemistry, especially organic chemistry, you have to think as if you have a crystal ball or if you have Parisians. So I'm not sure which pathway I need to take, so I will do both and then I see which is better. So suppose it undergoes an SN1 reaction, and as you have learned, SN1 means you have a two-step reaction, and in the first step, my pink marker says the bond of the leaving group and the carbon just break on its own. You form the chloride and you leave behind a carbocation, carbon with a positive charge, and all the other bonds remains intact. Okay? That's the first step for the SN1 reaction. Remember, SN1 is a two-step reaction. So this is just step number 1. Okay? Now the thing is, the driving force for SN1 reaction is the formation of a stable carbocation. But if you take a look, in this case, this cation here is a methyl carbocation. A methyl C+ is very unstable. It's of a high energy because the groups here that surrounds this carbon positive charge, they are just hydrogen. They are not electron releasing. So they are not able to suppress the positive charge of this carbon, which means to say that this is very unstable, which means is not formed. Which means to say that a methyl chloride does not like to undergo an SN1 reaction based on this reason. So if it's not SN1, it must be SN2. So now let's analyze why. In the SN2 mechanism, we know that the nucleophile will attack the alkyl halide straight away to the carbon and push out the leaving group. So here, let's use the nucleophile, NUC, okay, with the lone pairs of electron. And in the first step, the only step in the SN2 reaction, it will just pump in from the back and kick out the chlorine, which is a leaving group. Look at my orange arrow and drawings to follow the proposed SN2 reaction. Okay? Now in this case, if we do it in a slow motion, right, as the nucleophile go in, it will try to form a bond with this carbon, and as it forms a bond, it must break this carbon-Cl bond. So what we have is actually a transition state. A carbon in the middle, and then your H, they do not react, but the nucleophile here is trying to form a bond with this carbon. You see, that's why I use dotted line. And the carbon-chlorine bond is breaking. So you see, it's like a partial bond. So forming, breaking, pushing it out. So I put back this square bracket, and I need to add this dagger sign, a dagger. You know, you stab with a dagger. This shows that this species is a transition state. A transition state is not stable. It cannot be isolated, but the thing is, because it's not a real molecule, it is just what we perceive it to be happening there. It will just move on quickly and it will form the product, which is this. Now, why is SN2 good? Because your methyl chloride, in this case, only has 3 tiny hydrogens that surrounds the carbon that are attached to a leaving group. That means it's not blocking the way. We know that nucleophiles, they must contain lone pair, they have electron cloud. Dwaggy, you know, very big, so they will go in and they could avoid this small electron cloud to form a bond and kick out the leaving group. So that's the reason why SN2 is favored for a methyl halide in a SN2 substitution, nucleophilic substitution. So remember, to consider whether you prefer SN1, SN2, you have to try and consider these factors: electronic effect and the steric effect.